Since we are running quite late, probably we'll move to the next presentation that will be given by Dan McKenzie from Cambridge, the thermal structure of the Oceanic Lithosphere. This one is more.
I'll see if I can catch you up a little bit. I came into plate tectonics just as I finished my PhD. And unlike Xavier, I had no background in using observations to look at things. I was then very young. This is a picture of me at that age, which brought the house down in China when I said, this is my Harry Potter stage in life. This is taken at that sort of time in northwest Scotland. I've taken off my socks and kept my boots on because of the things to walk across this river. What I want to start by talking about is to take up where Jason left. This is a picture from that famous paper by Harry Hess, right, showing what caused us such trouble, which was the idea that spreading ridges here were underlain by upwelling mantle. Yes, but not now, we believe, by hot convecting sheets underneath the ridges. And what I want to try and do, first of all, is to get across, to try and explain why we had such trouble at the beginning understanding what was going on. Because now plate tectonics is taught in primary school. It's one of the easiest parts of geology, right, to understand. And what I'm always asked when I give talks like this is, why didn't we understand what was happening? It's so obvious. Well, it wasn't. It wasn't that we were stupid. The best people were trying to think about what was going on. We knew what were the critical observations, and we could not see how it worked. And this is largely responsible. Much of what Harry had to say in this paper actually is wrong. I don't agree with what Jason said, and particularly this idea, right, that there was a hot sheet underneath every ridge, really was one of the very hardest things to deal with. And so what I want to try and do is to take you back to that time. I agree with what Xavier had to say this morning, that once we had the observations, the answer was obvious, and actually who did what is of historical interest only, right? There were a whole lot of us involved, and we all did different bits of it, right? But the key thing was the observations. And the various of the problems, right, I'm going to illustrate various of the problems. This is a picture taken from Gutenberg and Richter's book in 1954, showing the earthquakes, right, in the Arctic. And no one, I think, would draw a spreading ridge on the basis of this, going from Iceland here across the Arctic. This is a modern picture showing the depth of the ocean. Here are the earthquakes, and anyone, primary school kid, would draw a plate boundary across here. But really, the location of the earthquakes was so bad, right, that we had really no vision as to what was going on. Here's a picture taken from Tuzo Wilson's a paper in 1963 showing what he thought were the ridges in the Indian Ocean. And some of them are right, but a lot of them are not. Here's the earthquakes. Right? You can see what happens is that there's a triple junction here with branches running like here. The data was just not there to get it right. And that was one of the real problems, right? It really became data-driven. This famous picture, which is still one of the best mapped regions of the world, Mason Raff's map of the Northeast Pacific. And this sat in the literature for a long time without anyone recognizing what they were looking at. The difficulty was, this is going to fail, I think. Let's see if I can get it to work by pressing it. The difficulty was that this, as Xavier said, the mapping of this was done by the US Navy because they wanted the bathymetry. The bathymetry was classified. So no one saw it except Harry Hess. Harry Hess was a rear admiral in the US Navy. He had seen this map. He was sharing an office at Cambridge with Tuzo Wilson, and they were talking to Fred Vine at the time. And Tuzo had worked out that the San Andreas was a transform fault, but it was offset, coming up here, from the Queen Charlotte Islands. And so Tuzo said, there has to be, how does it work? There has to be a spreading ridge in between. And Harry said, yes, of course there is, right? It's perfectly clear in the bathymetry. So Fred then went up to the library, fished out this, and recognized the symmetry. And that was really the beginnings of our understanding of what was going on. Here is then the bathymetry. Right? Here's the spreading ridge. Right? Here is the colored map that Fred then produced, right? Showing very clearly the symmetry. But nobody before that had recognized the symmetry, which is now so completely obvious from this colored picture. Information just was not there. Here are the earthquakes. The earthquakes, we didn't know where the earthquakes were. We knew they were offshore, but with the locations now improved by the worldwide network, put in to detect bombs, it then became clear what the geometry was of the spreading ridge. This is the Blanco fracture zone. This is the Queen Charlotte Islands. So it really was a matter of actually getting good data to see what was going on. This, which Xavier also showed, of the offsets, or Jason showed, of the offsets of on the fracture zones, actually, this offset by Victor Vaquier, who found it, Victor had actually gone out there to see if he could trace where the offset went to, because these ones were clear from the survey, this one was not. So he ran a cruise parallel to the Mendocino fracture zone here on both sides to look for the offset and found it. But this was totally mysterious. Right? There's no activity here on these fracture zones, no earthquakes. They run into the continental margin of California, but there's no offsets on land. Various people claim to have found offsets here from magnetic anomalies and stuff. All that's bogus. Right? There is no offset. There's no offset because actually the Pacific is moving that way, and has been for a long time, relative to North America. So the offset you should look for is not up here, but down here. But we didn't understand any of all that because we had no understanding of how triple junctions moved, any of all that stuff. Right? So we were completely at sea. The other problem, right, here's a picture of earthquakes beneath Japan. This is from 1965. You'd be a brave man or woman to draw a subducting slab on the basis of these earthquakes. Once we knew where they were, you can see it as clearly as anything. Right? It really was data dependent. Here's a picture from Gutenberg's thing of the profile across the North Pacific. He thought that he knew there were earthquakes, deep earthquakes around the Pacific, but here was what he drew, right, of the motions, that this was essentially a subduction zone. These earthquakes were caused by the relative motion between the region underneath the Pacific and that beneath Japan. And this is, what happened down here was just a complete mystery as to what happened below 700 kilometers. Right? This really doesn't conserve mass, so it's very difficult to see how this worked. It just really didn't make any sense until, essentially, Isaacs and showed that actually the earthquakes were confined to these slabs. It's interesting that the question in retrospect is, why wasn't this first recognized in Japan? Which I still think is one of the interesting questions as to, because they knew where the earthquakes were, though, as I just showed you, the locations were not very accurate. The paper that I published with Bob Parker in 1967, and it is interesting that it was the 30th of December of 1967. We sent the paper off in November. We got no referees' reports. We got no proofs. Nature just published it. Right? I don't believe that happens nowadays very often. I met the editor later on, John Maddox, and asked him about this, and he had no memory. He must have pushed it straight through, but he had no memory of having done so. It's really interesting. Right? I think this is a rotten display of the data. I really didn't know at that time how to display data clearly to show things. What I should have shown is this, which actually I produced. This is actually a redrawn copy of what I actually used in 1967, showing the slip vectors of earthquakes, right, which is what we used to get the pole. But the problem was, even then, with this idea of Harry Hess's, that there was a hot rising sheet underneath every ridge. And the difficulty you can see very clearly here, right? This is where the earthquakes are. If you keep the earthquake stationary and rotate the two continents together, and this is the Bullard fit, what you can see is that actually the present geometry of the South Atlantic matches the original break here. And that's fine in the Atlantic, but if you look at the earthquakes around Africa, you can see that there's a spreading ridge coming down here. This is the Mid-Atlantic ridge. There's similar spreading ridges in the Indian Ocean. Now, if these were the surface expression of convection, how did the convection cell here know that it should move at exactly the speed away from Africa to stay underneath the spreading ridge in the Atlantic and this one in the Indian Ocean? This seemed completely bizarre. And I remember having a conversation with Tuzo Wilson at Cambridge, and neither of us could understand, in 1965, neither of us could understand how this could possibly work. Right? It really seemed quite bizarre. And what about what happens on fracture zones? And when ridges jump? All this is completely mysterious if these are the surface expression of rising sheets. And this is essentially, this was drawn actually by my head of department in 1980, who was Ron Oxborough. He was a student of Harry Hess's at Princeton, and he still believed, even as late as 1980, that the ridges were underlain by rising hot sheets. Whereas by what I wanted to convince people of, but I didn't do it very well, was that actually the whole process on ridges had no deep structure at all. The heat flow, the topography, and later on the melting were just simply a consequence of the divergence of the plates at the surface. Now, if that's true, that puts an extremely strong constraint on everything that's going on, because everything then has to be the result just simply of the extension and not of any deep structure. And this really was the key to what I did next, what I then did, which was to take, I disagreed with Xavier, as he explained, so I took a simple analytical model and I did something very silly, which was to put numbers. I did the whole calculation in dimensionless units. I was a fluid dynamicist, but I put numbers for temperatures on it, and that was a mistake. And then I calculated the heat flow, and you can see the heat flow is extremely scattered. We didn't at all understand why. And I could get a perfectly reasonable fit. But this is really no more than a sketch. Xavier tried to do it. Xavier did it properly and drew the wrong conclusion, as he explained. I didn't really try and do anything. I didn't reckon this sort of data was deserving of trying to do anything accurate, so I didn't. And I didn't actually at that time do calculate the substance of the seafloor. This is from something which happened later on, which was that Barry Parsons and John Slater, essentially 10 years later, used the same approach, the same analytical approach, and showed, by that time we understood that the heat flow variation was due to the advection of heat by the water, by the black smokers. So they used particularly the subsidence, and came up with a model which then made perfectly good sense, which was a thicker lithosphere, higher temperature at the bottom. I was trying both to account for the heat flow and also to account for what we now call the elastic thickness of the plates with the same model, and you can't really do that. Their fit is quite interesting because they were very careful in what they did, and I was extremely impressed. I had not really taken on board until what they did. If you did everything really carefully, then it really had to fit. The geology was just like physics. If you did things properly, then everything worked out. And so indeed it does. They were, interestingly, in retrospect, just a little bit too careful. They would only use depths whose age they could constrain by the magnetic anomalies. This region in here is the quiet zone in the Upper Cretaceous, and they hadn't got any observations in there because they hadn't got any magnetic anomalies. So they missed something which later became obvious, which is that actually, no, the seafloor goes down, and then there's a bump here. And that bump is in the quiet zone. This is now a modern picture of the thing with taking not the analytical model, but now a numerical model, taking into account the variation of conductivity with temperature. The thermal conductivity changes by about a factor of 2 between the top and the bottom. You can see from the spacing of the isotherms. These are the depths of earthquakes, well constrained in the oceans. You can see they're all below 600 degrees centigrade. And that works even right up to the ridge axis. And the heat flow, now we remove all the ones due to the temperature from the black smokers, that also works. So I think we now have a really very good model of the thermal structure of the oceans. We can even do now a little bit better. Before I go on to that, the other thing which now matches came from worrying about the melting. On ridges, we need to generate 7 kilometers of oceanic crust, and we now believe we do that simply by decompression melting as the material upwells. Here is the upwelling. It follows an isentropic path here until it starts to melt. Then it melts. The deflection here is caused by the latent heat of melting. And you can see that the amount of melt you make depends very strongly on what's called the potential temperature, which is if you extrapolate these lines up to the surface, then that's the temperature which is marked on these. And you can see that by changing the potential temperature by 200 degrees centigrade, which isn't really very much, you change the amount of melt you make from 7 kilometers to nearly 50. So there's no problem at all in accounting for the thickness of the oceanic crust simply by decompression melting. You don't need any deep structure. The last part of this story is the most recent, which is that we can now look at the temperature in the ocean, in the oceanic lithosphere, by actually using surface wave tomography. And this is the thermal model, which I've just been talking about, which is taking into account the variation of thermal conductivity with temperature. This is a stacked picture of the velocities beneath the Pacific, stacked according to the age. And what you can see clearly here is that down to a depth of a bit more than 100 kilometers, you can see that the velocity changes as the plate cools, but beneath that, there is no change in the velocities at all. So this really shows more clearly than anything which I've shown so far that the ridges don't have deep structure. What you can then do is combine these velocities, which we measure from the surface wave tomography, with temperatures from the seafloor to actually plot the velocity against the temperature. And what you can see is that the velocity changes rather slowly with increasing temperature at low temperatures, and then very, very rapidly at the end. So you've got very good constraint. If you then parameterize this, you've got very good constraint on the temperatures at the high end of this, above about 1,000 degrees centigrade. So you can then use that. Here's just showing the fit, right, of the parameterization. You can see we do really rather a good job. Here's the misfit for the Pacific between the calculated and the observed velocities at 50 kilometers. This is from nodules, from the cratons. So we can actually now, I believe, convert the shear velocities, which are almost entirely controlled by temperature, not by composition, into temperatures. If we do that, this shows then the profiles of the temperature at different ages, calculated from the simple plate model, and that is what's shown by the red line, and the surface wave tomography, which is the blue line, but we've actually only got constraints at where there are dots. So all I did was just use cubic spine interpolation to produce a continuous curve. And you could see the agreement between up to about 65 million years is really extremely good indeed. Later, and this is essentially, now we're into the Upper Cretaceous quiet zone, you can see that from the surface wave tomography, the temperature is now slightly greater than it is from the plate model. And that then coincides, look at that, that's where the bump is. This is the bump. This is two efforts at looking at the variation of depth with age. You can see that the observations are actually quite scattered. This is the median, right? And there's some disagreement, but everybody agrees there's more to it than just a simple cooling plate model. The simple cooling plate model is the dashed line here, and this then is the depth age from Hoggard et al. This is from Crosby, and this is then from the shear wave velocities. So we can see now, right, that there's something else going on, which I believe is an instability of the thermal boundary layer as the plate cools, and that's what causes it to have a bottom to the plate. Right? The cooled material then detaches in some sort of convection. So finally, I've had a long career in this business, and these are the various people I've worked with. And the thing which I would really stress about the whole affair is the importance of the data. And I've always tried to work, quite a lot of these people are actually ones who've made observations, I've always tried to work with the people, once I grew up and stopped thinking like a physicist that all I needed to do was produce sketches, right? Once I actually was convinced, particularly by Barry Parsons and John Slater, of how much you could learn by really paying attention to the details of the data, I then have always tried to work with the people who make the primary observations, and especially nowadays with the geochemists, because the geochemical technology has improved quite astonishingly in the last 20 years. And now there's a huge amount of information there, which is not really being paid attention to by the geophysicists. And that's what I intend to do in my remaining and declining years. Thank you.